Okay, so let's start. Welcome to the next lecture from Effective Software. In today's lecture, I will talk about data races, some conditions. Slightly, I will touch the hardware architecture of the CPU units, and also memory system. I will talk then about volatile variables, which is quite similar in C language like in JVM. The next section will be about synchronization. Specifically, also I will talk about rentrand logs. After that, I will talk about atomic operations, support in the Java for atomic operations, how complex types are implemented. At the end of the lecture, I will touch non-blocking algorithms, and we will look to some data structures. So let's start with the data races. First, some initial example. Let's have this example. We have 4 variables which are shared across 2 threads, and each thread execute one method, method 1 and method 2. And these methods have the code which is written here. First, assign in thread A a value from the A variable into some local variable, then modify B, and later write that local variable into D. Almost similar things happens in thread 2, but with different variables. And here is my first question today. What can be the results for the C and D after these 2 threads are executed via this method? So any guesses? Or how many combinations see you there? Initially, all shared variables have 0 value. But as you can see, thread 2 assigned number 2 into A, and with that A, thread 1 may or may not work with, and vice versa. So what could be the outcomes after each thread finishes these methods? What is the result in C and D, because that's the last assignment in each method, assignment into C and D. Any guesses? If not, so let's go through that example. So one of the combination could be 0, 0, because you can execute and read into local variables before other thread modifies that other variable. So one valid combination is 0, 0. Then any of the intermediate combination, thread 1 can execute, for example, the full code of the method. Thread 2 executes slightly later, so then reads already modified B, 1. So that's another combination, 1 and 0. And the similar combination can happen in the reverse order, so there is 0 and 2 at the end. So that's visible from the code directly. But there is also one more combination which is missing because you have 2 values, 1 and 2. That combination can occur as well, even it's not directly visible from the source code. Why? Because if you look to the bytecode of the method 1, for example, very similar for method 2, but for method 1, you can see, okay, it's direct rewrite of the code in proper sequence, so that's fine. But during the compilation into native code for the CPU, you can notice this. The first operation is put 1 into field B, which is this one, the second line in that method, not the first one. Later, after that, there is a read into some temporary register. So there is this one instruction. And finally, put into field D is the last one. So what you can observe here, that during the compilation, there happened reordering of the operations because there are no dependencies between this line except R2. So this one is completely independent. That's why compiler can easily put it as its first, and then when temporary register is needed, it is compiled later into the code. From that, you can also notice that if local variable R2 is not used at all, that assignment will not happen even in the compiled code at all. So that's the reason after this reordering, very similar things happens in the method 2. That's the reason why the outcome could be 1 and 2 together, because it's a reorder. So first, both can assign new values and then use those new values. One more interesting thing in this, I've already last time mentioned several times the object structure which is on the heap. This gray area is object header, and object data is after the header. Header can have 12 or 16 bytes, depending on the size of the heap, whether compressed OOP is used or regular OOP is used. Class reference is with K, as mentioned last time, because it's internal representation of the class. So if you look here, write 1 into field B is write 1 into offset 10 hexa, which is 16. Why 16? In this case, we used heap size smaller than 32 gigabyte, so compressed OOP is used. So 12 byte is header of the object, and then object data is there. First is A, and second is B. Integer consumes 4 bytes. So offset 16 is the start address of the B field. That's it. That's easy. You can verify it for D. It's very similar. Let's look to the hardware infrastructure as well. So you should know already from different courses that CPU execution happens in a pipelined manner. It means that every instruction here is executed within several steps, and those steps are pipelined, so they are interleaved. While one instruction is fetched, then decoded, further instruction is fetched, and so on. And execution is happening after that, and so on. So the execution is in this pipeline manner. Even more modern CPUs does every step in parallel. Not just one instruction is fetched or decoded, but multiple, 4, 8, depending on the architecture. So if you look to the memory model, you should already know this as well. So here we have our cores executing instructions. We have L1, L2, and L3 caches. L1 and L2 are dedicated for every core. L1 is moreover divided into data and code caches, and L3 is shared. Access to the main memory is after L3. There are various sizes. Every time there is a minimum size which is cached, that's the cache line, usually 64 bytes or 128 bytes, depending on the architecture of the CPU. Size is increasing usually, but with increasing size, there is decrease of the latency, the speed of accessing the memory. All writes to the main memory are by default done in that write back mode, which means data is written into L1 data cache, then L2, then L3, and finally to the memory. And it remains all within those cache levels until there is no more space and it's evicted. So that means that standard write requires that particular address to be cached. So in that place, we have the measure of the cache miss. You should know already from the previous lectures about cache misses. But there also exist non-temporal writes, which bypass this mechanism and writes directly into external memory. Last time, I've also demonstrated optimization technique using prefetch instruction. And it's possible to instruct from the core the cache hierarchy to prepare some data into the cache without blocking. So that's about memory model. About execution, there is that pipelining I've already mentioned, but it's even more complex. For the CISC CPUs like Intel and so on, AMD, there is a superscalar architecture and superscalar execution. This is example of one core, and within one core, there are many execution units which can perform operation in parallel. In this particular Intel architecture, there is specifically 8 execution units which can perform operation in the same clock cycle. Because of Intel CPU or AMD, it is a CISC architecture, complex instruction set. Those complex instructions are first translated into micro operations, which happens here initially, and then those micro operations are executed internally, like do multiplication, memory read operation, memory write, logical operation, shifting, etc., etc. Within this architecture, independent instructions can be executed out of order, in CPU even. Even there is some sequence of instruction in assembly code, execution can happen out of order or in parallel if they are not using the same register or address. Even they are using some same register, but it's independent write to that register. Internally, there are no fixed registers in CPU. There are dynamically assigned registers positions. So write into accumulator register, 2 different writes can happen in parallel because there are internally assigned some logical register positions to that operation. What is even more important is that read operations themselves, memory read operations, are never reordered, but they can happen in parallel. In this case, 2 memory read operations can happen in parallel. In more recent architecture, even 4 or 8 operations can happen in parallel. They are not reordered, but can happen in parallel. Another thing is that later independent reads can be done before writes operation, because writes are usually slower. They're required, as mentioned on the previous slide, write back cache operation, perform caching before, and that's very expensive operation. So those writes can happen after reads which are behind those writes if they are not using the same address. Writes themselves are serialized as well, but again, there could be executed in parallel if that architecture allows parallel writes. So let's continue to the volatile variable, which uses internally memory barrier. So let's have our example like before, but just use keyword volatile for A and B. A is here in our example. And this is a resulting code after compilation, after just-in-time compilation into assembly code. So here we have read into temporary variable R2. Then we are storing 1 into B. And then there is this specific instructions which works as a memory barrier, write memory barrier. That is instruction having assembly prefix lock and then instruction, and that lock prefix forbids hardware infrastructure inside CPU performing any reordering around this instruction. That's one thing. And also performs like a flash of the cached writes, previous cached writes. So after that moment, any other core in that CPU, even core in different CPU in that architecture, should be aware about modification of some data in the memory. In this case, this lock instruction used addition 0 into stack pointer. That's a meaningless instruction because adding 0 into something doesn't modify that. And that's the intentional because it's the fastest write memory operation. It costs 0 clock cycle. It does just imply that CPU cannot reorder operations, memory operations around, and also performs flash of the cached values into other cache and also into external memory. So that's how volatile works. The same thing is applied in C language. If volatile keyword is used, instructions are not reordered during compilation, one thing, during the just-in-time compilation in Java case, and also during execution inside CPU. There is one more effect in a compilation, also in C language. That value, the read operation on that local variable or variable is always performed from the memory. So if there is previously cached value in some register, because many of the arithmetic operation, whatever, happens through the registers, if there is already some value loaded from that particular memory position, it's considered as invalid and new read operation happens from the memory. That's another effect of the volatile. So to summarize that, volatile variables are never cached locally inside the thread. All access goes directly to the main memory from the CPU perspective. It guarantees atomic read operation and atomic write operations because it defines a memory barrier causing that flush, not reordering, etc. It can be used for the primitives in case of JVM, or references as well, references to object. It doesn't block thread execution. It can consume more CPU cycles because that lock prefix causes flush of the caching, and that, depending on the amount of data which are modified locally, it consumes some CPU cycles, but that's not the blocking from the perspective of locks. On the other hand, these writes are much slower than the standard writes, so that's the reason why you should not put volatile everywhere. Depending on the cache size and invalid data there, it could be 100 times, it depends on the architecture. Also, volatile reads are slower because any previous write to the volatile cause invalidation of caching, and if other thread is reading the data, it has to go through all caches levels and read the actual value. But on the other hand, it's still faster than synchronization or locking. If you use in your code design patterns like immutable objects, where the data inside object is simply constant and created during the creation of that object, you don't need to consider this because then you don't need volatile property of any of that object field because it cannot be modified. Or if some variable is accessed only by a single thread, that's clear, you don't need to use volatile. Or where the variable is part of some more complex synchronization operation, like we will talk later during this lecture. So let's progress to the next slide. Here we have another example, volatile counter, which have a counter primitive integer, initially 0 value, defined as a volatile. We have getter, just simply get the counter value, and increment method, which use this counter plus plus operation. And here is my next question. Will this work like a real counter in multi-threaded environment? What do you think? We have volatile keyword there, so with two threads are calling increment on the same object, same instance of the object. What do you think? Is it going to work properly? and doesn't miss anything. As you can expect, because I am asking specifically for this, it is not working like a counter. Why? If you look to the assembly code of the increment method, which is interesting for us, you can see that first we are reading data from the counter into local register, then perform increment of that register, and then write that value back to the same counter you can see here. And after that, because we are using volatile keyword, any write to that variable which has a volatile keyword calls this memory write barrier. And that's it. So as you can see here, this plus plus operation is translated into 3 steps. Read the value, actual value, increment, and write. So it's not an atomic read, update, and write operation, but only atomic read or atomic write. So in this case, if 2 threads are executing the same code, both threads can read current actual value, both threads does increment, and both tries to write incremented value. And in this case, we are losing 1 addition because initially threads read the same value, not the incremented one. So that's the reason why volatile is not sufficient to implement counter. Yeah, and it's described here down on the slide. So on the other hand, for what it is useful to use volatile, for 1 thread writes and multiple threads are reading. So for example, a termination thread in some implementation, like you can have a thread pool where there are some workers threads, and those workers are usually cycles, while cycles, reading tasks from some queue. And there is also support for termination of the thread pool via some terminate flag. So those multiple threads are reading the same termination flag, which is implemented like volatile, but actually there is write only from some single place or rarely only from 1 place when the application is going to terminate. That's guaranteed that there is no infinite loop. If there is no volatile and you have some method while using that variable, it can happen that the value is cached locally inside the register, never read again, and that's then the problem, that you have infinite loops. So you need to use volatile to ensure that it's always, when it's read from that variable, it's always read from the main memory. So that was volatile for the primitives, for the simple data, or for the pointers. But what in the case that we have array? In our case, we have here an array of primitive integer defined as volatile. Here we have a constructor, getter for a value on some index position, and also put method. We would like to modify value on some certain position. Is this operation, which is mentioned here, the put, the modification, write into array, which is defined as volatile, considered to be safe atomic write operation? Similarly to the previous case, because I am asking here, the answer is no. Why? Because as a volatile, I've mentioned earlier that it could be primitive or the reference. What is the array in this case? Array is a regular object on the heap. So the volatile is just the reference to that object, not any manipulation with the value inside that object, only with that reference. And you can verify that in the native code. This code is more interesting because it works with the reference. Like I mentioned earlier, In our examples, we are using heap size smaller than 32 gigabyte. So we are using compressed OOPs. So you can see that here we are loading like a pointer from C language perspective, pointer to that object. Then we are using bit shift operation to the left 3 times, which is multiplication by 8. I've explained that last time, that all objects by default, the start address of the object is aligned to 8-byte address. That's the reason why we can easily address 32 gigabyte heap size using just pointers having 32 bits, which is by default 4 gigabyte memory only, because of the multiplication by 8, 32 gigabytes. So this is this shift 3 to the left. It's multiplication by 8. Then there is this check for array out of bound, because this is object which is array, so the header is longer. It includes also the size of that array to verify that we are not accessing outside. So that's happened here. From this, you can see that the array length is only 4 bytes. So you cannot create native arrays by design which are larger than 4 giga values because of this 4-byte limit. And then there is this sequence of value. Actual write happens here. RSCX register is a second input. That's the value we would like to insert. So this is the write using this complex operation like compute address, using this base address position. This is index, multiply index by 4, add this offset to the base address, plus add constant offset, which is this 10 hexa, and 10 hexa is related to this 16-byte header of the object. That's this last instruction here with the write. You can see there is no write, memory write barrier operation at all. So there exists some hack, some solution to that you can do this meaningless assignment, same value into the same value, and that cause that there is inserted, because this is defined as volatile, that reference, that cause that there is this write memory barrier instruction, which caused the flush of the caches, forbid any reordering around, etc. But again, like in the previous examples, it is not suitable for read, update, write operations, for complex operations. It's suitable only for atomic read or atomic write, nothing else. In order to fix our counter example, we can use synchronized keyword. That's something you should be aware of. You can have synchronized keyword within the method definition. Then it means that the whole content of that method is considered as a critical section. Or you can use synchronized code block using curly brackets. Then just the inside of the code inside the curly brackets is considered as synchronized. In this case, this synchronization happens on some single instance of the object. In this case, because we are using a non-static implementation of this method, the synchronization actually happens on the instance of the synchronized counter. That's it. If you have static, here the keyword, so the factory method, then the synchronization on the method level occurs on the instance of the class representation of that synchronized counter, not on the instance, because you can have many instances of the same classes. So then you need to consider on what you are synchronizing actually in the code. And in this case, everything inside is synchronized, but That's caused internally blocking, as you will see later. This is the fix for our counter. ++ is fully inside the critical section. On other hand, you can use rentrant logs. There are some benefits using rentrant logs. I will talk about these benefits later, but in order to rewrite this code into code using rentrant logs, you can use this pattern. So define a log in our object, which is rentrant log, and within this, where you would like to have a critical section, simply owning that log, you are using log operation on that rentrant log instance, and at the end, unlock operation. It's crucial here to use try and finally block. Why? Because if inside the block there is some kind of exception happening, if it is standard synchronized, that is handled automatically. That when there is thrown exception here, it automatically unlock owning locks. In this case, it's our own locking mechanism. So if we lock something, we need to make sure that we are also unlocking, otherwise there will be deadlock in our application. So if there is an exception here, it goes through the finally section, and we are unlocking that lock. How the synchronized is implemented inside Java Virtual Machine. Inside our object header, every object inside on the heap, there is this header. This is clear. The second argument is defined what type of data is that stuff. That's something which is not part of C language, but in Java, it's always ensured that we are not converting one object to another object without any intentional usage. So that every object instance has clearly defined what kind of object it is. That's this second part of the header. But the first part, there is this mark word, which is 8 bytes. And mark word definition is here on the left side. It's about 64-bit JVM. For the for the 32-bit JVM, it's slightly different, but it doesn't matter. It's almost not used today. So depending on the combination of the lowest 2 bits of that 8-byte number, it has different meaning, the value inside that mark word. What is interesting for us is combination 0, 1, which means unlocked. Object instance, so there is lock assigned to every object instance in case of Java Virtual Machine, and by default, that lock is unlocked. If it is locked, then there is 0, 0. It's fin-locked model. If there are multiple threads trying to lock the same object, it could be converted into fedlock system using operating system, and that's the combination 1 and 0. And depending on this, the rest of the mark word has some meaning. So there are also some lock records in a stack. So every thread in Java Virtual Machine has stack. There are frames. So inside that frame for the method which have synchronized keyword, block or method wise, or multiple synchronized, there are some predefined locations for every synchronized in that method, where there is a log record, and that log record contains this mentioned field. So there is the value from the original mark word, and also pointer to the object which is locked. So that's the way how, if you do debugging, debugger knows this thread is owning this log or pending acquirement of this log. That's why it uses this log records in the frames and knows which object on the stack is currently logged by this thread or not. The basic mechanism, the first one which is tried, is fin locking mechanism. So that's fastest locking mechanism using CAS, which stands for compare and set instruction, complex memory operation. which is applied to the mark word itself. So if some thread would like to acquire a lock on that object, it looks to the mark word. If it is currently unlocked, 0, 1, in the lowest 2 bits, then it can try to lock it into finlock 0, 0 using compare and set instruction on this mark word. If it succeeds, it means, yeah, you own this thread, owns this lock, and that's done. There are also these log records filling inside the code, but that's not important in our case. If it fails, it internally uses a spin locking mechanism, some cycles. Depends on the implementation of the virtual machine, also on the version. It could be 10, it could be more, using no operations to wait some time before it converts the locking mechanism on that object into fed locking mechanism, because that is more complex. You have to, in fed lock mechanism, you are using a monitor object, which is additional object instance on the heap, which is associated with the operating system locks, where the thread would like to acquire really some semaphores within that appropriate operating system where that JVM is running. And if that log is already locked by some different thread, operating system then makes sure that the execution of the thread is descheduled from the execution, it's put into waiting, and it manages all this overhead of thread synchronization. And that's very expensive. That's the reason why initially Java Virtual Machine tried to use fin locking mechanism, not the fed locking mechanism. The transition from fin locking to fed locking is using this inflating, because that is non-zero time to allocate operating system lock, create that instance on the heap, etc., etc. So one of the thread is trying to initialize everything, fill the values, and then try to acquire that thread. So if we look to the details here, this is simply the diagram of the state machine and transitions. So here we have an object instance which is unlocked. There are two types of unlock, as you can notice in this example. Because I haven't mentioned that before, for the combination 0, 1, the meaning of the rest of the values is, this is the age, it's used for garbage collection, bias, it's used for the some older version of Java for bias locking, which was recently removed since version 15. But the highest part of that mark word contains hash code. And if you create new object, by default, there is a 0 hash code. It means there is no hash code associated yet. You probably noticed in Java code that if you print from some instance hash code, you call it hash code method, and there is no override of that hash code, it automatically call a hash code implementation of the object, because every object in Java is based on the object class, and there is a default implementation of the hash code, and that the default implementation of the hash code generate initially that hash code value from the position of the object inside the heap. And that is stored here. So if for the first time, if there is a called hash code method on some instance, hash code value, hash code value is stored in the marked word. Why? Because there is a garbage collector which does a compaction of the memory at some later phases and can relocate objects inside the memory. So if you relocate the object, then if you are not storing the previous hash code, it can mean, oh, hash value will be changed. And then the contract, the equals contract, and all operation on hash sets, hash maps, etc., will be broken. So in order to preserve the previous hash code, Java Virtual Machine is storing that hash code inside the mark word. And it's here. And also this diagram shows what happens if you lock. It tries to change that to the fin lock. In that case, the rest of the mark word in the header is a reference to the stack, to the displacement of that, to that log record in the frame. And the original value from the mark word is stored there. Why? Because there could be the hash code. And so on. So the locking, unlocking is transition here. And also it could be inflated to the heavy locking mechanism, and that's the transition here. So now let's talk more about the rentrant locks. Why you should use or should consider usage of rentrant locks instead of standard synchronized keyword. They are providing this lock unlock, which is clearly mapped to the synchronized keyword, but there are some additional operations possible. Lock interruptibly. There could be interrupt called on that thread, which simply returns before lock is acquired. There is also try lock method. This method returns Boolean. If it succeeds, it returns true. If it fails, because that lock is owned by different thread, it returns false. And in your code, you can decide to execute something else. So simply not to waste the time in blocked thread, but you can execute something else. There is also try log where you specify the timeout. Try to acquire this log within 1 second. If it is not possible, say me it back and I will do something else. I will behave differently. That's doable also using rentrant logs. So there is a higher flexibility while using rentrant logs to implement more complex operations. Also, the locking and unlocking can happen wherever a method inside the code. While using the synchronized, you are limited to have synchronized just the single method or the piece of that method. While when using these rentrant logs, you can do locking and unlocking on different places. That's possible as well. Moreover, there is a fairness parameter of the rentrant logs. Fairness defines whether blocked threads waiting for that same log are in ordered or unordered queue. So simply fair log means it's ordered. So first first will acquire the log later. By default, rentrant log using the constructor without any parameter is unfair. If you would like to use fair, you should say they're true, and that means fair. Synchronized is unfair from the principle because there are those compare and set, fed locking mechanisms. So it can happen theoretically that if you have many threads going to the same critical section, it can happen that one of the threads will be waiting there forever because always some different thread will receive that log before that one. So in this case, you should consider usage of rentrant logs in fair mode. Next property of the rentrant log is that the default rentrant log, which is unfair one, is faster than the synchronized because it's internally implemented slightly different way. But on other hand, it's another instance of the heap. So it consumes some memory. And to summarize this, fair logs are much slower because there is an ordered queue and that has to be handled outside of the operating system different way, which thread will acquire the log and so on. So those are much more slower, but guarantee fairness between the competitors willing to acquire the same log. So now let's move to the next section, which is atomic operations. There exists also, to continue with our counter example, so we started with a standard counter, then counter using volatile, then counter using either synchronized or the rentrant logs mechanisms. Another option is to use atomic counter. Our atomic counter can utilize atomic integer That's the special object, which is part of Java framework, which guarantees full atomic operations on that object. So if we would like to increment our counter, we call increment and get method on this atomic integer, and it makes sure that it is thread safe and guarantee that we are not losing any increment of our counter. What is the difference? It's not using blocking inside. It's a first simplest non-blocking approach we are going to touch today, and internally how it is implemented. So if you look, this bottom part of this slide is the simply definition which is inside atomic integer. I've removed intentionally the enclosing class to have more space. So if you look here, there is a value which is defined as a volatile, fine. Here is our get and increment method, which internally calls an unsafe method get and add integer 2. This is a reference to instance of object. This is value offset of the field inside the definition of this atomic integer, which is defined here. So value offset is a static because it's same for all instances. It's a long. And again, it's using some unsafe. Unsafe is special way in Java virtual machine implementation to address some system-based implementation. In this case, operations accessing specific instruction on the CPU architecture. So here it gets offset of the value field inside this. So what it is, simply if we have standard object with this, and we are using heap size smaller than 32 gigabytes, you should already know that the header size is 12 bytes. So the offset for the only primitive here will be 12. If it is a heap size larger than 32 gigabytes, it will be 16. If it is array, the header is more bigger, then the offset will be again different. What is inside get and add int value? You can see here there is a while cycle. That's by the way, the main non-blocking pattern which is used for more complex algorithms. Like in this case. So first there is definition of some local variable, some precomputation, and then within the cycle it tries to get something. So in our case, because it's very simpler, it's just the atomic integer, it tries to read value from that volatile value into that local variable. And during end of the while cycle, there is call of compare and swap. That's the way how Java implements access to the compare and swap hardware instruction. And that hardware instruction works with many parameters. In our case, that's a reference to the object. Then the second argument is the offset of that value. So simply those two are added internally. Then this was what we would like to increment within that value. So we first read the previous value into variable 5. That's this one. So the next parameter is what we are expecting. We are expecting that on that memory address, there is still value which we read previously. And if it is there, we are expecting that we are writing that value increased by the provided argument, which is 1 if we do increment. So if there was, for example, number 5, this is 5 and this is 6 then. So, and this returns Boolean. If it succeeds, then it returns true, this cycle ends, and we are done. If it fails, it returns false, and the cycle is repeated again. And that's the basic non-blocking pattern. We are expecting that something is true, and if not, let's repeat the whole cycle. If it is still what we are expecting, then it passes and we are done. And internally, this instruction ensures that if this is executed on different core within the CPU or different thread, or even different core within a multi-CPU computer or system where this is running, it ensures that the modification on the same address is really atomic. So it reads the value, makes sure it matches what is expected, and if yes, the only single thread modifies that value and returns the flag saying, yeah, I am the one, I've modified the value. All other threads at the same time will fail because only the single thread can modify that exactly same memory position. It looks complex just for the simple thing like atomic integer. But actually, if it gets compiled on, for example, the CISC architecture like Intel is, you can see this is the result of assembly code of that increment method. And what you can see here is that it first gets the current value here, just gets the, that's not the value, that's the reference, because it's then used for testing whether it's null, because Java always throw null pointer exception if you are accessing something which is not pointing to real object. So that's the test here. If it is null, it's throw null pointer exception. And the whole content of that increment method and get is this instruction, lock prefix, we already know that. But then there is not meaningless value, but rather addition 1 into some certain position. So if the architecture where the virtual machine is running support more complex atomic operations, those are natively used. And the whole while cycle is translated into single instruction, even very complex, but single instruction. That lock prefix still works like a memory barrier, so it forbids the reordering around. It also calls flush of the previous writes from the cached values into external memory, so it's visible by other CPU, but also ensures that the core at the moment when the instruction behind the lock, this one, the addition, it makes sure the hardware architecture that it has, the core has exclusive ownership of that appropriate cache line inside the whole system. So there exists this cache coherency protocol, you should be aware of that, called like a massive. Massive is just shortcut of various states in that protocol. Modified, exclusive, shared, invalid, or forwarding. And in our case, exclusive, that's E here. So it has to first, the CPU has to, in its own L1 data cache for that particular cache line position, get exclusive flag. And only the single core, single cache in the whole CPU or even multi-CPU system can own exclusive flag on the same address. And that's done by this lock prefix. So this is the only thread which can own exclusively this address. And what it's own, it's perform increment of that address to 1. And at the end of that instruction, it tries to make sure the flush operation so that address will see that. So if two threads are willing to execute this instruction on the same address, one succeeds first. After it completes the operation, the second one can continue. So the atomic integer-based counter, on the other hand, is the fastest implementation of the counter for multi-threaded usage. It is not suitable for single-threaded usage. Why? Because it's still using this lock prefix by design. And if only single thread, in majority of cases, is doing the modification of the counter, that will be affected by the speed of that lock prefix. to acquire exclusive cache line position, etc., etc., it's cost a lot of CPU cycles. If you are using a synchronized counter, in that case, when in majority of cases single thread is going to manipulate that, it could be faster. But if many threads is going to use that, then atomic integer is faster than the synchronization, which typically in such case result into blocking of threads. So it's deschedule execution of the thread in the operating system level in the scheduler, put it into queue. Then if log is acquired, it has to schedule it again for the execution, and that's extremely expensive operation. So to summarize these atomic operations, the very basic atomic operation which is available through all architectures of CPU is CAS, compare and change instruction or exchange instruction. It depends on the particular implementation. By default, 32-bit hardware CPUs support this compare and exchange, compare and set instruction of 64-bit operation. 64-bit CPUs support compare and set on 128-bit values, so it's always 2 times bigger, working with some register pairs, for example, and larger memory areas. There is one drawback in Java. So in order, because there still exists a 32-bit implementation of Java, a virtual machine, so in order to make things easier, it internally used just 64-bit compare and set operations. It is not utilizing this 128-bit atomic operations. So we can easily cover by 64-bit all this: atomic boolean, atomic integer, atomic long, atomic reference, integer array. Then the atomicity happens on the value at particular index position, atomic long arrays, and also atomic reference arrays. You can notice that there is nothing like atomic double or float. That's because there is usually a coprocessor in some older architectures used, and that's even more harder to make sure that cross various platform it will operate in atomic manner, so that's not supported. On other hand, we have to say that any instance here, if you would like to use atomic integer, it's atomic with capital A, and that means it's object. So every single instance is one object on the heap. And every object, as you should know, there is a header, and the minimum overhead is 12 bytes. So for atomic integer, which is just 4 bytes, we need to consume 16 bytes of our memory. That's the drawback. And if we have code where we have millions of atomic integer instances, then it counts, because we have 12 million overhead on that. And that's not good to waste our memory, which is relatively cheap, but still we are wasting memory which can be used for something else. And also, if we have still enough memory, wasting of the memory causes more frequent garbage collection cycles, slowdown of performance of our application, and so on. So what to do in this case if we have a lot of instances of whatever value, for example, atomic integers? There exists atomic field updater. So that's suitable for the cases where you have a large number of objects of given type. So for example, our atomic counter, and we expect that during the runtime of our application, there will be really large number of the instances of that atomic counter. Then the code, the original code, where it's called here object with atomic, which internally use value, which is atomic integer. And if we have some method and works with the value, we can call increment, compare and set, and whatever we need atomically on that value. So if we have a million instances of object with atomic, we have also a million instances of atomic integer, double overhead. that could be converted into this, where we change this object-based thing into primitive, but define it as a volatile. And then this is static, so there is just a single instance of this for whatever number of instances we have of this atomic object. And we are using this field updater, atomic integer field updater, which is typed on this object. And it's some kind of handle to work atomically with some particular value. In this case, we are working with this value. So that's the handle to work with the value. It internally have an offset and all other stuff, but there is just a single instance of this, not million instances like in previous cases. And if you would like to work atomically, like in this case here, we are just calling that updater, that field updater, and passing more parameters, and that's the pointer to the actual instance of the object. It's internally ensured that we are applying this field updater operation to proper object instance, that is particular type, but then it implements exactly what we want. So in this case, if we have million instances of this object with atomic, there are just million object plus one only, not like million plus million in the previous example. So that's very efficient from the memory perspective. But as mentioned, internally the execution is slightly less efficient. Why? Because it has to check whether the type of the object which is used for the within the call, this object, typed object. We already know from the previous lecture that the generics in Java are implemented the way that it is used just for the compilation of the source code, not for the execution. For the execution, it's used internally descriptors, and those descriptors are using object type. So internally there is object always here, because it can accept whatever it's needed. So it has to ensure that it's appropriate type, perform the checking, and if yes, then the operation is called. But on the other hand, as you know from the previous lecture, there is a lot of optimization techniques inside Java virtual machine, inside just-in-time compiler. It can get eliminated quickly just for the checking of the type object, and that's one lookup. There exist atomic field updaters for the integer, for long, and for references. Unfortunately, there are no field updaters for the arrays, but if you have array with million element, it is considered, okay, you probably don't have million arrays with million elements. So then it's not needed. So it really depends on your use case, whether you need a field updater or you can use array, which by design already supports atomic operation on every item element there. Aside, there are also more complex types. Atomic markable reference, so it's a object reference along with some mark bit, so true, false. Atomic stamp reference, again, atomic reference along with the integer stamp with additional 4 bytes. Why? There exists ABA problem. What it stands for? It's simply the mechanism of the problem which describes the mechanism. So if you have some algorithm which use that expected value, and if expected equals what is actual there, perform the modification. But theoretically, what can happen during the execution is that I'm expecting A, but in between someone changed from A to B, later someone from B to A, but there is still A at this moment, and it can cause invalidation, corruption of some data structure, even though the value I'm expecting is still there. That's the ABA problem. So that problem could be addressed using this, for example, integer stamp. So any modification, there is some kind of increment, and even the value is one time increase, then decrease. The same value is still different because it's always also verified that that stamp equals. If stamp is modified, we have to repeat our typical non-blocking pattern again. On the other hand, as mentioned earlier, Java virtual machine, in order to have a variety or support for many platforms, it doesn't support double wide compare and set instructions. So this cannot be easily internally implemented with 128-bit compare and set, but rather just the 64-bit compare and set operations. Then it implies that if you would like to have 64-bit reference and 32-bit integer together modified at the same time, we have to use something more complex. And in case of Java virtual machine implementation, is object allocation. So you can, instead of changing the values, you can change the reference to some object which contains many things together and consider those many things together as immutable and having that combination of stuff. So how it is implemented inside, this is just the example of atomic stamped reference. So there is integer. There is some internal object class definition, pair, which contains reference and the stamp. It has constructor, it's final, so it's immutable. And it has factory method to construct that. And then that atomic stamp reference, instead of having those components, it contains pointer, just the reference to the pair object. So anytime we would like to perform compare and set operation on those combinations, we are using our known pattern, and we are creating new pair, and then call compare and set cycle, which is internally the cycle of that new reference and previous reference. And that's it. That's here. This is the current reference, and this is call of the factory method. So actually, that's the reference to the new combination. So that's how it is internally implemented. So it's not that efficient as it looks like. So anytime you would like to have something really efficient, you have to consider this problem, and maybe you don't need all 64 bits. You can, like Java, you can design or dedicate some bits for a counter, for the stamp, and implement it your way. That's how internally non-blocking algorithm does it. So we already shown atomic operations, but internally there was the simplest do-while cycle with the basic non-blocking pattern. The non-blocking algorithms by design are lock-free. That means it's non-blocking. There is no synchronization. Nothing which can cause that the thread execution will be blocked for whatever reason. So there is no lock. There could be retry, but no lock. And as you notice in our example, there is do-while cycle. There is no guarantee on the number of loop iterations. It depends on the concurrency level in your application. So by design, non-blocking algorithms are not wait-free. Wait-free algorithms, on the other hand, have different properties, saying there is a finite number of steps where it is guaranteed completion of that operation. So the lock-free is not sufficient to guarantee finite number of steps. That wait-free is needed for real-time systems and also for some critical handlers in operating system, like interrupt handlers. It cannot happen that it will cost millions of CPU cycles. No, it should be extremely fast. Otherwise, we are going to lose data from network. We are not going to consume data coming from the block devices, whatever. Non-blocking algorithms are based on compare and set, compare on exchange, or the instruction with the lock prefix, which is usually the case in the modern CPUs. Because why you should consider to use non-blocking algorithms? If you are having some thread-safe implementation based on the synchronization blocks, there have drawbacks. High priority threads can be blocked, So interrupt handler cannot enter the section because some lower priority thread is doing the execution. Locks are unfair, for example, by design. If you use fair locks with fine-grained locking mechanism, there is overhead. And all this locking can lead in deadlocks, because you can usually lock several locks in different order, and that could cause that there are some deadlock situation. Or the priority inversion, I've already mentioned, some lower priority thread holds the lock for longer than expected. On other hand, non-blocking algorithms do not use any locking. They are based on compare and set, or compare and exchange instruction, where if it is not massive concurrency, they usually succeed on the first try. So that cycle is executed just once, the do-while cycle. If there are two threads at the very same position of the code, okay, one of them repeats. That's it. So it removes the cost for the synchronization, thread suspension, even more complex context switching of the thread, the scheduling thread from the execution from particular thread, run something else, then put it back. So let's look how such more complex non-blocking algorithm is implemented. I have two examples. One of them is stack. What is stack? Stack is a LIFO data structure, last in, first out. Most recent value is first removed from that structure. So let's first define some internal structures like node. Node has item, the value inside the stack. It's used generic, but it doesn't matter in this case. And for the linked list, it uses this next pointer to the same node structure. And then here we have a constructor for that, because it's a final for the value. Then inside that stack, we have one thing, which is atomic reference, and it is called head. It's the pointer that's reference for the head object, the one which is on the top of that stack at that moment. If there is nothing, that's null. So how now the push operation, push something into that stack, occurs? I've created some new head candidate here. With our item, we would like to put it there on the top of that. And here we have our well-known do-while cycle. So we attempt to read the previous head. That's the head which is currently there. Remember that head operation, it's illustrated here, by the way. This is our new object. So initially, we try to store previous head into our next reference. That's this link. And then, at the end of the while cycle, we are using compare and set. If there is still old head, put there new head. If it succeeds, let me know. So it tries to exchange this reference. Expect this value there, so ensure that it will be the second value, and put there my new candidate. If two threads are calling this, one succeeds, second fails. If it fails, what it does, it just reads the new head, update this reference, and try it again, and so on and so on. So it will guarantee that our data structure is not broken, and every time only single thread succeeds to push new value to that stack structure. The pop, the reverse operation, works very similar. Some definition of local variables, our well-known do-while cycle, read the head. If that head is null, it means it's empty, okay, returns immediately. Try to prepare a new head, which is simply old head next reference, and try to perform compare and set operation. If there is still old head, store that new head. That's illustrated here. If it succeeds, it means, okay, I am the only thread which just popped this object from our stack structure. So that in that case, return the value from that object. If it fails because someone else modified the header reference, okay, repeat the cycle. Read the new reference of the head and try again. So if any number of threads are then calling push and pop, it guarantees that data structure is not broken and it correctly works. There is no synchronization needed and it's very efficient. On the other hand, if you have some shared data structure which are used rarely, it's not that effective to use everywhere non-blocking algorithms because of compare and set instruction. And what you will see later on some next lecture, there is some optimization technique related to the synchronization. If only single thread is calling some piece of code always, synchronization is eliminated completely. But if there are really multiple threads accessing and modifying same data structure, then non-blocking algorithm is your way. So to summarize that, there exists thread-safe collections and maps. You can either use blocking collections and maps, just there are some decorator mechanism, synchronized collection, some factory methods returning some different instance, which internally does just the thing that there is put synchronized to every operation. And that's it. So decorates by synchronized all operation of particular type of collection, list, map, set, and so on. So you don't need to do it yourself. So that's the way how you create blocking collection and maps easily in Java. On the other hand, you can use this non-blocking collection and maps. They are called slightly different, but provide you operation you really need: linked queue, linked queue, concurrent hash map, concurrent skiplet map, and so on. Internally, it uses atomic approach. So there is no synchronization unless it's really, really needed. And this is still valid, like I mentioned on the previous case. If you don't have that concurrency, it's then better to use standard collections because of elimination of the synchronized keyword. In this case, if we are really having multiple threads, it's better to use non-blocking version because there is no synchronization, no blocking, and no overhead of context switching and so on. So let's look to detail of one such data structure, like a concurrent hash map. You should know how standard hash map is working. There is some internal class inside entry. That entry contains key value usually, and also some next to the entry because there could be conflicts. And the basic data structure of the hash map is hash table. And if you are inserting some value into the hash map structure, first hash code is taken from that instance of the key. That is used to compute index in the hash table. And then, if there is no conflicts, it's inserted the reference to that particular key into that hash table position. Actually, there is entry object as well, because if there is some collision, some hash code collisions, so multiple instances which are different, are pointing to the same, let's say, index in the hash table, then that collisions is solved by linked list internally. So that's how the standard hash map is working. Concurrent hash map works very similarly. So you have top-level hash table, which is this structure. In our case, to simplify it, we have size of 4 only. So if we are inserting some objects, we are again computing hash code. Using that hash code, we are usually call modulo to count the remainder of the division, to point to some position in this hash table, and then it tries to insert the data into that hash position. If there was previously nothing, like null, which is initial state, it succeeds immediately. The main difference between concurrent hash map and standard hash map is that the modification of this is done using compare and set instructions. So it's done automatically. atomically. So in standard hash map, you have to use synchronize in order to not to break and don't to lose any data which is inserted. In this case, you don't need to do synchronize because it prepares the data and then tries to call compare and set of reference in this hash table reference position. If it succeeds, okay, I am the only one inserted there. If I fail, someone else modified that same element. So there is some contention level, some concurrency level inside this data structure, and that equals to the size of this hash map or hash table inside. Because if there are hash collisions, there is very similar manner of the linked list inside, using that entry next records, and this is then done to simplify it, not to use compare and set everywhere, because if you are traversing linked list to find the end of the list to add something new, someone else can modify that list. So there is a synchronization. So it's not fully non-blocking, but it's non-blocking on the top level only. But it's usually sufficient because by default, initially, the size of the hash table in hash map and also in concurrent hash map is 16. So in fact, the concurrency level is 16 as well. 16 threads can succeed if there is proper distribution of hash code, which should be there. 16 threads can succeed without any blocking. If there is hash collision, okay, synchronization can occur. Segment contention, so the value on the same thing, is implemented the way that it used linked list, as mentioned, if there is less than 8 elements. If there is more elements to speed up finding inside that long list, there is used balanced tree structure. So there is some kind of tree structure inside to speed up the find operation, because then its complexity is logarithmic instead of size. There is also table resizing defined for the hash map structure, for this concurrent hash map structure, with the occupancy factor, by default 0.75. That's the same, by the way, like for the standard hash map. What it means, if you insert, so initially there is 16 hash table size. If you insert there more than 12 key value pairs, it implies resizing of hash table. The resizing happens here very same way like for the hash map, power of 2, always double the size. And during that, rehashing has to occur. It is done in parallel fashion in case of the concurrent hash map. It's reusing nodes if that is not changed, then it uses some kind of forwarding node. So if there are 2 threads trying to put there more data, they can help each other to speed up resizing of the hash map. That's slightly different than in standard hash map. In standard hash map, you have synchronization and the second thread is completely blocked, and only single thread is taking care about resizing. That's fine for small sizes of the hash map. But if you have hash map with millions of key value pairs, then it takes time. So if you have 2 threads, 3 threads, you can divide the work and speed up really the resizing operation. You can also provide initial capacity like for the standard hash map. If you know that you have a concurrent hash map or hash map structure where you are going to insert 1 million elements, to avoid many sequences of resizing, which is expensive operation, which always call hash code and so on, you can initially say, yeah, create this internal hash table with million size already, or you have to divide it by the load factor. So if it is million, you should put there more than a million, because you avoid this expensive table resizing. Moreover, in case of concurrent hash map, this initial capacity also affects concurrency level. So if you put there million, then yeah, for sure, there will be much less hash code conflicts, collisions. So the parallelization level on the top level will be the fastest possible. And that is the very last slide I have today. So thank you for your attention, and we are at the end.